Okay, so we want to discuss ratio test, which is section 6 from Ben's packet. We're going to be looking at ratio test. Actually, I'm going to say probably 3 times. Right now we're going to do an introduction to ratio test. Later on we're going to find ratio test when we're doing series of constants, and then we're going to come back and do ratio test again to get a little bit more information than we're going to get here. Essentially what I want to know is when we were looking at sine x and cosine x, it seemed like the more terms I added, the longer my hug went on between my series and, or I guess, the polynomials and the true function. It looked like we had a guess that it seemed like they were going to hug each other forever if I added on more and more and more terms to my series. But for 1 over 1 minus x, that geometric one, it seemed like that hug was very finite. It was a short little hug. Okay, and ratio test is essentially going to tell us how long that hug is. Okay. Okay, so it tells us how long our series will hug the function it is approximating. It's essentially telling us how long the approximation will be good for, okay, for what values of x the approximation will be true, okay. We, like I said, have some options on this. We sometimes see that the hug goes on forever. Sometimes it's a short hug, sometimes it's a big hug. Sometimes we're not going to get a hug at all. Sometimes we're just going to get a kiss and they're going to move on with their lives. Okay, so we have some options in terms of what we can get in terms of these. Well, let's get some terminology on this first. Let's talk about the interval of convergence. The interval of convergence is what I've been calling the hug. Okay, it's how long the series approximation is true to the function. Okay, so the interval of convergence, again, is the hug, or the interval on which the series is true to the function it is approximating. Okay, so we saw for sine x, it seemed like that hug went on forever, from negative infinity to infinity. For cosine x, the same thing. But for 1 over 1 minus x, that geometric series, that it seemed like it was a short hug, that it only seemed like it was happening from like negative 1 to 1. Okay. Okay, so these are the 3 series that I just mentioned. We have sine x, cosine x, and 1 over 1 minus x are geometric series, okay? And it appears that sine and cosine have an interval of convergence that lasts forever. So how would we write out what that interval would be? Well, we would write it from negative infinity to infinity, okay? So for sine x, it appears that, and we're going to prove this in a second, that the interval of convergence goes from negative infinity to infinity. For cosine x, that the interval also goes from negative infinity to infinity. Okay, but when we were playing around with 1 over 1 minus x in class, it seemed like it was only hugging it from the values from negative 1 to 1. And that actually really makes sense in terms of what this function is. Okay, this being a geometric series, it's only going to converge if absolute value of r, in this case absolute value of r, the ratio between terms would be absolute value of x, is less than 1, and that's concurrent with the interval that we are saying, which is going from negative 1 to 1. Okay, so let's talk about what ratio test says, and then we'll talk about how to use it and what the possible answers are for these intervals of convergence. Actually, before we even go on to that, we also need to talk about a radius of convergence. Okay, so we said the interval of convergence is the hug, or the interval on which the series is true, okay, to the function that it's approximating, so where it's coinciding with the function that it's approximating. The radius of convergence, well, if you think about the radius of a circle, it's half the length of the circle, half the diameter of the circle. The radius of convergence is going to be half the length of the interval, okay? Okay, so the radius of convergence is half the length of the interval, or the distance from the center, or the kiss, to one end of the interval. Okay, let's talk about some options for what we can get for these values. Okay. So let's talk about our possible answers for this. We already saw for, let's say, sine and cosine, that it seems like the interval of convergence would be from negative infinity to infinity. Okay, and if that's the interval of convergence, how big is that interval? Okay, so maybe pause and think about it and come back. The interval would be infinitely big, and then what's half the length of that? Well, half the length of that would be infinity. Okay, so when my interval of convergence goes from negative infinity to infinity, my radius of convergence is going to be infinity. Okay, one option that we haven't spoken about is that sometimes our series is going to be pretty awful to approximate the value of a function, and they'll only agree at one single point at the center. Okay, if I only agree at one point, the interval won't have any length to it. So the way that I write that is this. Okay, I do curly brackets with an A inside, A being the center of the series. So if it only agrees at that one point at the kiss, and a series will always agree with the function at the center. Okay, at the kiss. They will always kiss each other. It's just whether or not there's any hug involved is the question. But so if my interval only contains a single point, how long is that interval? Well, the length of that interval is 0, so half that length would be 0 as well. Okay, the last situation is more like that geometric series situation where we have some interval, and the interval is centered around the center, centered around that kiss, that I'm going to have agreement with between my series and my function. So let's actually start with the radius of convergence on this. Okay, if our radius is just some finite value, okay, so instead of being a forever hug, it's a short hug or a slightly longer hug, but for sure a finite hug. So the radius is just some number. The interval of convergence, as of right now, we are going to say we don't know for sure. And we'll talk about why we don't know for sure in a minute. But right now we're just going to say that it needs to be determined. Okay, so as of right now that if my radius is some number, my interval is going to need to be determined. We'll figure that out later when we put everything, all of our information together. Okay. Let's talk about what ratio test actually is. Okay, the ratio test says, what if series who are not quite geometric actually kind of somewhat behave a little like geometric series as you go out towards the end of the series, okay, as you keep going in the series. So the whole idea of a geometric series is that there's a ratio between terms, and if you think about what ratio means, it means that you're dividing one term by the next, right? And if you divide in a ratio, geometric series, if you divide one term by the next, you'll get your ratio. So let's look at that. Okay, so here I have the ratio of two consecutive terms, and if you take the ratio, I put absolute value bars there because it doesn't matter if the terms are positive or terms are negative, but if I take the ratio of two consecutive terms in a geometric series, I'll get the ratio of I'll get the R part of the geometric series. Okay, and we've been looking at absolute value of R anyway. And I said that even if our series doesn't actually behave like a geometric series, there's a possibility as you go out towards the end of the series that there's kind of a pattern to the terms. So let's talk about how do we get out to the end of the series? Well, we let n go towards infinity. So I would have my limit as n approaches infinity, the absolute value of the ratio of two consecutive terms, okay? And what ratio test says is that if I'm behaving like a geometric series as n gets big, so I don't actually have a geometric series, but as n gets really, really big, I'm kind of behaving similar to a geometric series, then similar to a geometric series, if this limit is less than 1, the series will be convergent, just like with the geometric series. If this limit is greater than 1, the series will be divergent, just like with geometric series. If absolute value of R is greater than 1, the series is divergent. The only time, because we're not actually dealing with a geometric series, is that if this limit gives me 1, my test fails and I don't know anything. Okay, which is part of the reason we can't pinpoint the actual interval of convergence at this moment in time. Okay, so again, if the limit equals 1, the test fails because it's not an actual geometric series, and we need more info. Okay, so that's what the ratio test says, that if I take the limit as n approaches infinity of the absolute value of the ratio of two consecutive terms, and I get a value less than 1, the series will be convergent. If I get a value greater than 1, the series will be divergent. And if I get a value that equals 1, the test fails. Okay, so let's actually start by ratio testing one of our friendly little series, and we'll see what the interval of convergence is and what the radius of convergence is and how that all makes sense. Okay, so I want to show that sin x, or the series that approximates sin x, is actually good if it's an infinite series for all values. So we're going to use our ratio test to do this. And what you're going to be asked is to find the radius and the interval of convergence, and we're going to be able to find both in this particular situation. Okay, ratio test is to take the limit as n approaches infinity, the absolute value of the ratio of two consecutive terms. Okay, now if this is my general term for sin x, then a sub n is not too bad. A sub n is just this part of this. Okay, and a sub n plus 1, I'm going to replace all my n's with n plus 1's. Okay, so what I'm going to have is this. Okay, so I have the limit as n approaches infinity of a sub n plus 1, which I just replaced all my n's in my general term with n plus 1's, and divided by a sub n, which is just my general term. Okay, that's how I do ratio test. All right, I want to simplify this. And while I'm simplifying that numerator there, well, hang on. I'm going to simplify my numerator, and then I'll deal with the fact that I've got a fraction divided by a fraction. Okay, so my 2 times n plus 1 plus 1s become 2n plus 3s. So I have negative 1 to the n plus 1, x to the 2n plus 3 over 2n plus 3 factorial, divided by negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, and I have absolute value, and I'm taking my limit as n approaches infinity. First of all, with those absolute values, I can just totally disregard these negative 1 to the n plus 1s and negative 1 to the n terms, okay? I don't need to simplify them or do anything with them. All they do is create positives and negatives, and I don't need any negatives in my problem, so I can just completely disregard them. For what's remaining, if I want to take this limit, I need to look at the fraction divided by the fraction as the first fraction times the reciprocal of the second, so I'm going to rewrite that. Okay, and this is already looking much better. So I have the limit as n approaches infinity of x to the 2n plus 3 over 2n plus 3 factorial. Instead of divided by that other stuff, I have multiplied by its reciprocal, so times 2n plus 1 factorial over x to the 2n plus 1. Okay, this is really why we have, we worked on factorials in that sequences section in the book, because I'm going to want to simplify these, the 2n plus 1 factorial and the 2n plus 3 factorial. I'm also going to want to simplify the x to the 2n plus 3 and the x to the 2n plus 1, okay? So I want to simplify like terms that I have there. Let's talk about those x to the powers. I can do it two ways. I can, and honestly this is, I'm realizing, not the best example to start with, but here we are. So I can either do a simple division and realize that x to the 2n plus 3 divided by x to the 2n plus 1, I'm going to be dividing things that have exponents that have the same base, and if I have the same base I can just subtract exponents, and I would have, I'm going to do this, x to the 2n plus 3. Okay, note that we have that if we, x to the 2n plus 3 divided by x to the 2n plus 1 would be, if I just subtract exponents, I'd have a 2n minus a 2n, which would give me 0, and a 3 minus 1, which would give me a 2, so I end up with an x squared. If I don't like to do things that way, I can rewrite the bigger exponent to be a product of the smaller exponent and simplify that way. It's totally up to you. I think this way is much easier, but we can also do it this way. Okay, so the other way to think about it is to write x to the 2n plus 3 as x to the 2n plus 1 times x squared, and the reason that those things are the same, if you look working backwards, is because if I multiply the exponents, if I'm multiplying those bases, I'm adding the exponents, and I would get x to the 2n plus 3. And then if I have that commonality, I can divide these out to 1, and I end up with the same x squared that I had up here. Okay, so regardless, when I simplify these two blue pieces, I have an x squared for that part. As far as my factorials go, okay, when I look at, and I'm just doing this right here so that on the side so that we can really talk about it, but normally I would just be doing this within the problem. I wouldn't be doing this so exclusively, but I just want you guys to see what I'm looking at, what I'm focused on, what I'm simplifying. So when I'm trying to simplify factorials, you always write the larger factorial as a product of the smaller factorial. So 2n plus 3 factorial is larger, and 2n plus 3 factorial means 2n plus 3 times 1 before it, or 1 less, 2n plus 2, times 1 less 2n plus 1, times 2n times 2n minus 1 times 2n minus 2, and so on all the way down to 1. And once I hit that 2n plus 1 times 2n times 2n minus 1 all the way down to 1, that happens to be the same thing as 2n plus 1 factorial. Okay, so that's why I'm going to be rewriting this as 2n plus 1 factorial divided by 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, and now my 2n plus 1 factorials divide out to 1, and I end up with 1 over 2n plus 3 times 2n plus 2. Okay, so now the other thing that we need to talk about is what are the implications of this limit. Okay, I'm taking the limit as n goes towards infinity. All right, is that going to affect any of my x's? Think about that. Okay, if I'm letting n go towards infinity, does that affect what's going on with x? Especially if my blue stuff here, my x to the power is simplified to be an x squared. Is the limit as n approaches infinity going to affect x squared? And the answer is no. All right, I've got 10 seconds before a bomb explodes on me, so I'm going to stop this and start in video number 2. So see you video 2.